All right, so we were talking last time about how if you have an expanded octet, then you might have to identify its shape, its geometry, based on a chart of this nature, okay? So, let's just get that a little bigger, okay? So here we can see that for instance, this situation right here, we have a central element, okay, surrounded by 1, 2, 3, 4 other elements. It's bonded, and then a single double bond. I mean a single lone pair. And so in that situation, you would be bonded to 4 things with a lone pair. Normally you'd say if you're bonded to 4 things, you'd be tetrahedral. Okay, but in this case, you're bonded to 4 things, and you have a lone pair on the central element. Therefore, that disrupts that tetrahedral shape, pushes these bonds down away from the lone pair, and you end up with what we call a trigonal bipyramidal shape. Okay, I don't expect you to remember trigonal bipyramidal, but I do expect you to remember linear bent, trigonal planar, trigonal pyramidal, and tetrahedral. Okay, so anything else, you would just be able to identify it from the reference material. Let me show you what that looks like, the reference material. Okay, so this is the same one that's in your book. It looks like this. Okay, it's very well organized into this chart based on, you can see here, the number of electron pairs. That's including bonds. So here, 1, 2, 3, 4 bonds, and a fifth one could either be a lone pair or a bond. So in the earlier example, we saw that it was a lone pair. In this one, we're assuming that it's a bond. Okay. Okay. Nope, never mind. I know what that says. No, that's 5. That's 5. I'm sorry. That's 5 bonds. Okay. If it was 4 bonds and the lone pair, then we would see this shape. Okay. And so we're identifying that through the number of lone pairs up here versus the number of things that are attached to it, including lone pairs. Okay, so if you have 1 lone pair, 4 bonds, you would be seesaw shape. If you had 2 lone pairs, 3 bonds, that would give you a total of 5. You would have a T shape, okay, etc. And that's how you would use this chart, okay, to identify your shape, your geometry. Okay. All right. So if we're going to predict the molecular geometry, first thing we have to do is draw the correct Lewis structure, because it would be very difficult to identify it without drawing it. Okay. Count the number of lone pairs on the central element, number of atoms bonded to the central element, and then you would use Vespers or your chart to identify the geometry of the molecule. Okay. So, carbon dioxide. Just looking at this molecule, it'd be very hard to tell me what its geometry is, okay, without drawing the structure of it. So, we would say carbon, 2 oxygens. Carbon has 4 electrons. Each oxygen has 6. 6 times 2 is 12. That's 16 valence electrons in my structure. Carbon bonded to 2 oxygens. Start everything out with 8 electrons. Could this even have an expanded octet? Could it even be possible for it to have an expanded octet? Nope, because carbon does not have a third energy level. It only has two energy levels, the first and the second energy level. And the second energy level does not have a D sub-energy level, therefore it cannot expand its octet. So we could not have an expand octet on carbon. Okay. So if I'm going to draw this molecule, I count the number of electrons that I have in the structure right now, which is 20. Okay. And then I reduce the number from 20 to 16 by making bonds. So I'll make a bond here, and I remove electrons, lone pairs of electrons from each of the elements that I bonded to. That allows me to maintain the rule of 8, 2, 4, 6, 8, 2, 4, 6, 8 on each of the oxygen and the carbon. Now I'm at 18 electrons. So I make another bond, and I remove electrons from both of the elements that I bonded to. What is the geometry of carbon? It's linear. Okay? If you make two bonds, 0 lone pairs, that is linear. Two bonds with lone pairs, it could be 1 or 2 lone pairs, 1 or 2 lone pairs. You will be bent. 3 bonds, zero lone pairs. What's your shape? I don't have any lone pairs on the central element, but I make 3 bonds. We know it's trigonal because it's 3 things, right? Say it again. Planar. Trigonal planar. Three bonds, 1 lone pair. That's going to be trigonal what? If you make 4 bonds, no lone pairs, you will be tetrahedral. Okay? So, essentially, this is what I want you to know. You won't have a reference guide for this. I would expect you to be able to identify those based on the number of bonds and lone pairs that are on those compounds. Okay? All right, so that's the end of Chapter 7. Chapter 8 and Chapter 7 are going to kind of go hand in hand. So to finish that homework assignment, we have to understand a few concepts in Chapter 8. Okay? Not a lot, but we still need to identify a few. Yes? It is, well, it was due on Monday, but I changed it to Wednesday. Because Chapter 7 and 8 will not be on the test. It will be on the final. Okay? So with that homework assignment that I gave you, I'm going for the final, for Chapter 7 and 8, for the final, what I will do is I will choose, I think it's like 4, can't remember exactly, 4 or 5 of those compounds from that sheet. And I will ask you the same questions about them on the test. Okay? So you don't know which 4 or 5, you need to do the whole homework assignment, you need to make sure you're doing it correctly because those are going to show up on your final. Okay? 4 or 5 of them that you'll have to draw and answer the questions about. Okay? How many sigma bonds, how many pi bonds, what's the formal charge of the elements, etc. Okay? So you make sure that you do that homework well and correctly. It will be due next week, Wednesday, which is our review day for our final. Your test will be on Monday, but it will not cover 7 and 8. Okay? 7 and 8 will not be on there. Okay? All right. Let's look over chapter 8. So we'll finish up chapter 8 here. We'll probably have a little time to, I'll print up the review for the test, and I'll hand it out, and then have a little time to maybe go over some of those things if you need to. Okay? All right. So chapter 8, it's advanced ideas of these covalent bonds that we know about. We know covalent bonds are formed through elements that are like-minded and that they want to gain electrons. And so instead of one stealing the electrons and the other one giving it away because they both want to gain those electrons, they just end up sharing those electrons. Okay? So with that idea that they're sharing those electrons, okay, comes a lot of different properties that we end up having, like polarities and nonpolar molecules and those kinds of things, okay? So here they're just showing that we have these oxygen molecules, and if you put them between these magnets, okay, then they will, this is a kind of oxygen gas that gets trapped here, and you can see they're all kind of doing their own thing here, but here they actually line up according to that magnetic field. So there are some properties there that we don't quite understand, and we're going to try to understand how these covalent bonds kind of come into play. Okay, this is just the idea that you have these hydrogens, and you have the distance between them, but then as they start to share those electrons, those nuclei get closer together. Okay, all right. So here's an example of the types of bonds that you can identify on these molecules. You're going to have to be able to identify and tell me whether a bond is being made is a sigma bond or a pi bond. Okay, and that has to do with the fact of whether it's a hybridized orbital or a non-hybridized orbital that is bonding. And so that goes into the concept of, well, what is hybridization? Okay? So, but here we see that we have an overlap of a p orbital, okay, with another p orbital, and that would give us one type of bond. Here, this would be more of a sigma bond. Okay. Here we have two s orbitals. They're coming together, and they are forming that sigma bond. Here I have a p and an s orbital, and they're coming together, and they're forming that sigma bond. Okay, same thing here. Okay. So these are sigma bonds that we're forming. From the overlap of either an S and an S and a P, but these are all, the idea here is that these are all hybridized orbitals, and we're gonna understand that concept a little here in a minute, okay? But when you get P orbitals that are unhybridized and they overlap, that's when you get what we call a pi bond, okay? So here you can see these orbitals are coming together, and they're forming this pi bond. Now remember that p orbitals kind of form that dumbbell shape, the nucleus in the middle, okay? And the electrons are orbiting in kind of that dumbbell shape. And so that's why with that dumbbell shape, if you get two p orbitals that are unhybridized coming together, they will form this pi bond. Kind of, this is a single pi bond with two overlapping areas of electron density. Okay? And that's what we refer to as a pi bond. Now, how do you identify it on your drawing? Okay, the way that you would identify it is if I'm making a single bond, that is a sigma bond. There are no pi bonds here. The only time you would get a pi bond is if you have an unhybridized orbital that forms a double bond, okay, or a triple bond. So here I have a sigma bond. You always have one sigma bond in every bond, okay? But the other bonds, so if it's a double bond, are pi bonds. So here I have one sigma and one pi. So this is probably my sigma, this is my pi. Okay? In the triple bond, I have a sigma and two pi bonds. So you always only have one sigma bond, the other bonds are pi bonds. So sigma, sigma pi, sigma pi pi. And that's how I would identify it on my structures. Okay? So, what type of bond is this? Sigma. This one? Sigma, right? Let's just do that. Okay? Do I have a sigma bond here between the carbons? Yes. Okay? I have one sigma and one pi. What's this one? This is also sigma, right? So everything that's a single bond here is a sigma. So how many pi bonds do I have in this structure? Just two. The rest of them are sigma bonds. Okay? So here we can see kind of that idea of some of these. Okay, so what is this, a pi or a sigma bond? This is a pi bond because we have the overlap up and down between the dumbbell orbitals. Okay, maybe this is a energy level 2 and this is energy level 3, but they're still overlapping at that. Okay. Okay, so these are pi's, but they're hybridized and they're coming together in a different way. So what would we say this is? Sigma or pi? This would be sigma, okay? Because we're only coming together here. We're not coming together up and down like this, okay? What's this one? Sigma. That's a sigma, okay? That's how we would identify those. Okay, so here we have an s orbital and a p orbital coming together. What type of bond? Sigma, right? That's a sigma bond. Sigma bond, sigma bond. This could maybe something like water here. Okay, making those two sigma bonds. Okay. Yeah, this is water. Okay. 2p orbitals of oxygen with the 1s orbitals of the 2 hydrogens. Okay, making those sigma molecules. Okay, and that's where you get those geometries come into play. Okay. All right. So that's how we would identify those. Now, hybridization occurs when you take a pi orbital and you change its shape. Okay, it hybridizes into a new type of orbital. So one of those lobes kind of comes down in energy, and the other one kind of and you get kind of a middle ground of an energy level. Okay, of a sub-energy level, and so it's changing the shape of that orbital, which brings it into a hybridized state. Okay, and it would look something like this if you were going to draw it in this fashion. So here I have a 2s and a 2p. The 2s is lower in energy than the 2p. But if I hybridize, okay, into an sp orbital, All right? The hybridization brings the P and the S into the same sub-energy level. Meaning the S and however many P's I need, I don't always grab all the P orbitals, I just grab some of them. And I hybridize them into however many I need to spread my electrons out. So for example, think about carbon. Carbon has 2 electrons in the 2s, right? I should just draw it like that. Sorry. And then it has 2 electrons in the 2p. If this was true, how many things could carbon bond? How many things could it bond to? It has a pair of electrons here. It only has free electrons where? In the 2p. It only has 2 free electrons. Carbon does not commonly make only 2 bonds. How many bonds does it commonly make? 4. Well, how does it do that if it only has 2 free electrons? It does it through hybridization. Carbon is probably the most common example of this hybridization, and once you get into organic chemistry, you're going to see it quite often, okay, that these are going to hybridize. So this 2s and this 2p, this 2s comes up, 2p comes down, okay, and I get 1, 2, 3, 4 hybridized orbitals that allows for all 4 of these electrons. So this is the sp3, 1s, 3 p's hybridized into the same sub-energy level, which allows for 1, 2, 3, 4 unpaired electrons. And that's how they'll fill. So hybridization allows for the electrons to spread out so that they can bond now to more things. So carbon makes this type of bond very commonly, okay, which is an sp3 hybridized bond. Okay, so it's just showing you how these 3 orbitals are coming. They're hybridizing from here to here. They're hybridizing, and you get a different middle ground hybrid energy state. Okay. All right. Okay. This is an electron deficient molecule. Boron is. So what is the hybridization here? So boron is making 1, 2, 3 bonds. Boron has 2 electrons in the 2s, right? And 1 electron in the 2p. So it's forming, though, 3 bonds. 3 sigma bonds. Sigma bonds are always hybridized bonds. So if we go back and look at double bonds or single bonds or triple bonds, if we're going to identify the hybridization of those bonds, we would always identify the sigma bond as a hybridized bond. Okay? It's a hybridized bond. Sigma bonds, and then also lone pairs. Lone pairs are always in hybrid orbitals. They're always in hybrids. The only things that are unhybridized are those double or triple bonds. Those are in the unhybridized orbitals. Okay? And they would not count as for hybridization when we're looking and counting hybridization. So here, boron, if I was going to ask, what is the hybrid state of boron? Is it sp? Is it sp2? Is it sp3? sp3 would take all 3 p orbitals. sp2 would only take 2 p orbitals. sp would only take 1 p orbital and combine it with the s. Okay? So the question here is, how many hybridized orbitals does boron have? Well, these are all sigma bonds, right? So it has 3 hybridized orbitals because all 3 of those are sigmas. So if it has 3 hybridized orbitals, that means I need to take the 2s and how many p's? Just 2 of them. And then I have 1 unhybridized p orbital, but I don't care about that because I don't even have anything in it. So I have 1, 2, 3. So what is the hybridization here? It's sp2. The hybridized state of boron is sp2 because it's making 3 sigma bonds. No lone pairs. If I had a lone pair on boron, that would cause it to be in the sp3 hybrid state. So all you have to do to identify hybridization is count. You just simply have to count the number of lone pairs and the number of sigma bonds that you have, and that will tell you the hybrid state of your molecule. Okay? Okay, so here's sp2 is the hybridization of that boron. That's what we got to, that sp2 hybrid state. This is where it started out. It hybridized so it can make 3 bonds, because otherwise it could only make 1 bond. It only would have 1 individual electron that it could bond with. Okay? What is the hybridization of this nitrogen? We have to count. How many sigma bonds are on the nitrogen? 2. How many lone pairs are on the nitrogen? On the nitrogen I have 1 lone pair, right? So how many hybrid orbitals will I need? 3. Sigma and lone pairs, you count them together. How many hybrid orbitals do I need? 3. I need 3 hybrid orbitals. 3 hybrid orbitals will be what hybridization state? 1s and how many p's? 2. sp2. sp2. Okay? So that nitrogen is in the sp2 hybridization state. What about this carbon? Same, sp2, right? Because I have 1, 2, 3 sigmas. I have 3 sigmas, 1 pi. The pi bond is the unhybridized orbital. So I have sp2. How about this one? What's this carbon's hybridization? sp2. What about this carbon's hybridization? sp2. All of these are sp2 hybridized. Okay? You simply have to count the number of sigma bonds and the number of lone pairs to identify the hybrid state. Okay? For that sp2 state. So this would be sp3 because I have 4 orbitals here, 1 s and 3 p's. Okay? And that would cause my carbon, like in methane, CH4, CH, H, H, H. That would be in a sp3 hybridized state because it's making 4 sigma bonds. That means it has 1 s and 3 p's. And that's its hybrid state. Okay? Okay. Okay, now look at this sulfur. This might be a little trickier, but what is its hybridization? Count the number of bonds and lone pairs. How many sigma bonds do I have? I have 4 sigma bonds, right? 1, 2, 3, 4 sigmas. And how many lone pairs? 1. So what is its hybrid state? 4 sigmas, 1 lone pair. How many hybridized orbitals do I have? I have 5. Okay? Now the thing about p's is I can only have 3 of them. Once I get past the p, where do I end up? In the d. So where do you think that 4th orbital is coming from? Or I should say the 5th. It's coming from the d. So we would say this is S, P. How many p's? 3, D. Right? I have 1 from the D. Can sulfur do that? Does it have a D? Yes. Sulfur can do it because then it can expand. So this is an expanded octet. So expanded octets would take from the D. They can hybridize up into the D. Yeah. It's just for purposes of understanding the geometry of it, or to draw it in more of a geometrical way. So like this one is coming out at us, this one's going into the back away, and these ones are just on the paper plane. Okay, that's what those are mean. Just trying to give more detail about its shape, but they just simply mean bonds. Here they just drew the line. Okay, what is the hybridization of this one? Okay, 1, 2, 3, 4, 5. I have 5 hybridized orbitals. So SPD. Let's see, SP3D. That's going to give me 5. So you just have to make sure you're counting the number of orbitals to match the number of bonds and lone pairs that you're making. Sigma bonds and lone pairs. S, that's 1. P3, that's 4. D, that's 5. Okay? This one is missing a lone pair. I'm making 1, 2, 3, 4 bonds, but I still have a lone pair, so that's still 5. Okay? So that's 5 hybridized orbitals, sp3d. Okay? So these are all sp3d. Okay? sp3d. So 1, 2, 3, 4, 5 bonds, and I'm in the sp3d hybridization. Okay? 6 would take from 2 Ds, and if I made 6 bonds, or if I had 4 bonds and 2 lone pairs, and I had 6 hybridized orbitals, that would be sp3d2. sp3d2. That would be my hybridized state. Okay? Let's see. Okay. So what is the hybridization of this molecule? Of this selenium in this molecule? That's what I should say. How many sigma bonds do I have there? This is a lone pair. sp3d. Right? 1, 2, 3, 4, 5. So sp3d. 1, 2, 3, 4, sp3. 1, 2, 3, sp2. 1, 2, sp. Okay? What is the hybridization of this nitrogen? So I have 1, 2, 3 sigma bonds, 1 lone pair. That's 4 hybridized orbitals. S and 3 p's. sp3. What is the hybridization of this carbon? Well, let's count the sigmas. 1, 2, 3 sigmas, right? No lone pairs. So what is that? sp2 to have 3, right? This is that's a different element. So what is the hybridization of the oxygen? sp2. 1, 2 lone pairs, 1 sigma bond, sp2. Okay, and we already did the nitrogen over here, so it's the same over here. sp3. sp3. Hybridization. Okay, so it's not that bad once you understand just how to count them. Okay, and then trying to identify what they are. Okay, carbon here has what hybridization? sp2. This oxygen, what hybridization? sp2. This oxygen, sp3. 1, 2, 3, 4. 2 sigmas, 2 lone pairs, 4 sp3. Right? This carbon is sp3, has 4 bonds, 4 sigma bonds, so it's sp3. Okay? 1, 2, 3 sigmas, sp2. And the other one would be the same. Okay? So that's what we need to do for the hybridization. So if you look at your homework assignment, okay, that I gave you, that homework assignment that I gave you. Anybody else need one?
So sorry.
Trying to reach too far. Across. Anybody else? Okay. Okay, so look at number 1, BeCl2. Draw the structure, identify the molecular shape, identify the hybridization of each element in the compound, and show the overall dipole moment if there is one. Okay? So, BeCl2. Beryllium surrounded by 2 chlorines. Is this right? How many electrons do I need in this structure? So I have 2 chlorines, which are 7 each, right? So that's 14. And beryllium, which has 2, so that's 16. Okay, I have 20 in my structure right now. So if I made them like this, I could get rid of electrons here, and here, and here, and here. Now I have 16. Is this my structure? We made a big mistake from the very beginning, which is a common mistake. What do we know about beryllium? It only has 2 valence electrons. So can I put 8 electrons around beryllium in the very beginning? I can't. So let's start over. Okay? Boron and beryllium, common mistakes that are made with those two. You cannot put 8 on boron. You can only put how many? It has 3 valence electrons, so that means you can only have 6 electrons around it. Okay? So Be, Cl, Cl. Okay, this has 16 electrons in it. That's my structure. Okay? Identify the molecular shape. What is the shape of this molecule? Linear. Okay? Determine the hybridization of each element. What's the hybridization of the chlorine? sp3. 1, 2, 3, and a sigma. That's 4 hybridized orbitals. So it's sp3 to have those 4. So that means this chlorine is also sp3. What about Be? What's the hybridization? sp. Only 2 hybridized orbitals, right? So that's the hybridization of Be. Good. Okay, let's look at formal charges. What is the formal charge of chlorine here? Now, what we know about this molecule is it has to end up being 0 because there's no charge on it. Okay? So, but what's the formal charge of chlorine? I can't hear you guys. Well, let's see. So it's I have 7, right? Valence electrons. Okay? So let's count down 6, 5, 4, 3, 2, 1, 0. It's 0. So that means this chlorine is also 0. Be starts out at 2, 1, 0. This is also 0. Everything's at a 0 formal charge on this molecule. Okay? So the formal charges are all 0. Okay, dipole moment. So dipole moments are the polarity of it. What's more polar, chlorine or beryllium? Chlorine is more polar, or I should say it has a higher electronegativity. What has a higher electronegativity, Be or Cl? Cl has a higher electronegativity. Okay? So the question here is this molecule going to be polar, nonpolar, and what is its dipole moment? So the dipole moment is showing which way the electrons are going if you have a polar molecule. If you have a nonpolar molecule, then there is no dipole moment. Okay, that's how we would describe it. Nonpolar, no dipole. Polar, dipole moment, and the dipole moment will be shown as an arrow in the direction of that moment. Okay? So here we would say we have electron going this way. So from Be to Cl, okay? You don't have to draw this because in the end it's going to end up not having a dipole moment. So, but I'm just showing you that this is a polar bond between Be and Cl. So the dipole moment, if it was just Be and Cl, would be pulling the electrons towards chlorine. So we would draw it like this. Okay? However, because I have a chlorine over here too, it's pulling with the exact same force, right? So it's a tug-of-war for electrons. If I am having a tug-of-war with myself, who wins? Nobody wins. That red flag stays right in the middle because we're both pulling with the exact same force. So if I have a polar pull this way and a polar pull this way, then I end up just causing those electrons to stay put. nobody wins the tug of war. So the electrons don't move. If your molecule has a perfect distribution of the elements, then it'll always be nonpolar, because nobody wins the tug of war, because everybody's pulling for electrons with the exact same force at the exact same distance away from the nucleus. Okay? So because all that pole is the same, it's nonpolar. So this is a nonpolar molecule, nonpolar, no dipole. Dipole. Okay? No dipole moment, because it's a nonpolar molecule. So I wouldn't show any dipole moment. I'd just say it's nonpolar. It's no dipole. Okay? Now, if you had a molecule like this, nitrogen's pulling for electrons. Nitrogen is pulling for the electrons away from the hydrogen. Okay? And to represent the dipole moment on this, I might actually draw it more like this, showing the hydrogens are down, this lone pair is up. Okay? Which way is the dipole moment going? Where's the electron density being pulled towards? It's being pulled away from hydrogen towards nitrogen. The lone pair is also contributing to that pull, and so you have a straight upward pull for the electrons here. That electron density is getting pulled away from those hydrogens up towards the nitrogen and the lone pair. Okay? A lone pair always has electron density pulled towards it. So this would be the dipole moment here. This is a polar molecule. One way you can identify a polar molecule from a nonpolar molecule simply is because it will have a lone pair. A lone pair indicates a dipole moment or a polar molecule because it has disrupted the symmetry. So if it was like this, nitrogen, hydrogen, 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 and it was trigonoplanar, these hydrogens are all distributed perfectly away from each other. So the nitrogen can't pull in one direction, okay? Because those hydrogens being exactly away from each other wouldn't allow it to. So this would end up being a nonpolar molecule. A better example than having a nitrogen there would be a more accurate one, I should say, is boron, BH3. These hydrogens are perfectly distributed around that boron. Nobody wins the tug of war. The electrons stay put. This would be nonpolar. Okay? C, H, 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 H. No lone pairs, perfect symmetry. So because I have perfect symmetry around this carbon, it's nonpolar. Methane is a nonpolar molecule. Methane gas is nonpolar, which gives it a lot of its characteristics. If you're nonpolar, then you're usually gas at room temperature. There are some polar molecules that are gases at room temperature, but a lot of polar molecules, if they're big enough, are solid at room temperature, or liquids. They won't be in the gas phase. Because being a nonpolar molecule, it means you don't have attractions between your molecules. But if you're a polar molecule, then you attract to one another, and it becomes sticky, and that causes you to be in more of a liquid or a solid phase rather than a gas phase. Okay? But things like oxygen, nobody can win here, right? So this is a non-polar molecule. Anytime you have a diatomic molecule like H2, N2, O2, F2, it's always non-polar because there's no dipole moment. Nobody can win the electron pull. Okay? Nobody wins. Water. What would the dipole moment look here? Anybody guess what that would look like? So just a single dipole moment going in which direction? Towards the oxygen, away from. So think of these as, being one kind of area down there. And the dipole moment is going this way, towards the oxygen, away from the hydrogens, okay, and towards those lone pairs as well. So the dipole moment would be drawn this way. That's where my dipole moment is going. The electron density is going here. So if we looked at electron density map of this, we'd see this is starting to become partially positive here, and this area is becoming partially negative because the electron, the dipole moment is coming this way. Okay? Away from those hydrogens. That's how I would identify that. Is this molecule polar or nonpolar? This is polar because it has lone pairs on the central element. And those lone pairs have disrupted. They have disrupted the pull for electrons. What's the dipole moment on that carbon dioxide molecule? What's that? Okay, so it would be towards oxygen. But what do you notice about that? Exactly. So this is is there a dipole moment? No. No dipole. So if you get a nonpolar molecule like carbon dioxide is a gas, right? Room temperature. Because it's a nonpolar molecule. It doesn't have a dipole moment. All right? So it ends up being nonpolar, no dipole associated. Okay. And I think I handed a review sheet out to you guys, right? Yes. Who needs one? On Monday. Anybody else? What's that? Oh, it shouldn't say final review. You guys found my secret. I have a final review. I cut it up to give it out for each individual. Should say test 3. And then I'll give you the final review, which will basically be all 3 reviews. Okay.
And the final is not the next one. It's the next one.
Right. I think that's the 8th. Yes. Oh, okay. Oh, sure. Formal charge. So what is the formal charge on this carbon? The formal charge is identified by just counting the number of electrons and the number of bonds. So actually, let's look at this oxygen. It'll be a better example. Okay. So non-bonding electrons, I have 1, 2, 3, 4. Bonds, I have 1, 2. So that's 6 things surrounding that oxygen. Okay. And oxygen has how many valence electrons? 6. So if it has 6 things surrounding it and it has 6 valence electrons, that means it's at 0. Okay? So the way I would do it is I would start, if it has 6, I would say 5. 5, 4, 3, 2, 1, 0. Okay? And I would count down. So for this carbon right here, it starts at 4, has 4 valence electrons. I would say 3, 2, 1, 0. That carbon is also at 0. Okay? Okay? What is the formal charge of this carbon? 3210. What is the formal charge of this oxygen? 543210. So 0 and 0. What is the formal charge of this oxygen? 543210, negative 1. 543210, negative 1. Negative 1, negative 1. Carbonate has a negative 2 charge. So that makes sense. The formal charge is consistent with the negative 2 charge of the carbonate. Okay? So there's a number of ways that we can draw this phosphate molecule, but let's look at the formal charges based on the ways that we draw it. Okay? Formal charge on each oxygen there is 5, 4, 3, 2, 1, 0, negative 1. Negative 1, negative 1, negative 1, negative 1. This has what charge? Phosphate has a negative 3 charge. What's the formal charge on the phosphate? On the phosphorus, excuse me. Phosphorus has 5 valence electrons, so I start counting at 4. 4, 3, 2, 1, positive 1. So that makes it work. It's a negative 3 charge on the phosphate, on the phosphorus. Okay. Okay. Each of these oxygens would have negative 1 charge. Okay. 5, 4, 3, 2, 1, 0, negative 1. Each of these oxygens would have 5, 4, 3, 2, 1, 0. These are at 0. And then the central phosphorus, which should have a 5 valence electrons, 4, 3, 2, 1, 0, negative 1, has a negative 1 charge. So I have 3 negative charges there. That's negative 3 phosphate. Okay? So you need to make sure that the formal charges equal the overall charge of your molecule. You have to equal the overall charge. Okay? Any other questions? Okay, look at your review. Is there anything you want me to go over on that review? Enthalpy. So enthalpy, we can calculate enthalpy in a few different ways. Okay. Delta H is equal to products minus reactants. Now, if you know the delta H of formations of your molecules, then you can easily find the enthalpy of the reaction by summing the enthalpy of formation of your products, the enthalpy of formation of your reactants, and subtracting those, right? So whenever the delta H of formation of an element that is in its elemental state is what? So what's the delta H of formation of hydrogen here? 0. Of oxygen? 0. The delta H of formation of water would need to be given to us, right? We'd have to look that up. It'd either be given to us in the question, or we would find it on a reference material. It'll be in the question because I don't put that reference material for you because it's in the question. Okay. So delta H of formation of H2O, and this is in, let's say this is in liquid phase. If it was in the gas phase, it would be a different number than in the liquid phase. We're going to say it's in the liquid phase. Negative 325 kilojoules per mole. Okay? And so then knowing that, I would take the products. Here, all I have is products because the delta H of formation of H2 and O2 are 0. Okay? So would the delta H then be negative 325? Almost. What am I missing? I'm missing that it's for 2 waters instead of just 1 water. So in this reaction, I need to account for. So the delta H of this reaction would not be negative 325. It would be negative 325 times 2. So I'd have to multiply that by 2 in order to find the delta H of this reaction, being products minus reactants, and my reactants are 0. Okay? So negative 650 would be my delta H. Okay, subtracting 0. If these delta H's did add up to something, then I simply subtract them from negative 650. Okay? Yes?
Can we do one where it's like the 3 equations and you have to set them up instead of 1?
Yeah, I can try to find one.
Yeah, I was gonna set that up.
Let me see. Chapter 5. Okay, so something like this, right? Calculate the center enthalpy of formation of liquid methanol. Hold on. Methanol. Okay. Might be a better example. Oh yeah, this one's a better example. Okay. Calculate the heat required when 2.5 moles of A reacts with excess B and A2B according to the reaction. Okay, so first we want to find, here's the reaction, right? We want to have this equal this to find the delta H of this reaction. Okay, let's see if this will work. Did you freak out? Okay, it's not going to let me do that. Okay, so here what we want to look for is what do we have to do to these reactions so that it'll match this reaction, right? So we have 2A, that matches. B, that matches. A2B is in the wrong place on this one. Okay, we want it we want it to be on the other side. But we do have it on the other side in this other one right here. Okay, which is good because we've only got one A2B here and we only need one here, but we have two here and we have one there, so this one cancels and that leaves me with just one A2B here. Produces 2AB, which is what we want, and A2. So I really don't have to manipulate this at all. It actually equals that reaction. Okay, so to find the delta H of this reaction, I just simply have to add those together. So 25 plus 35, negative 25. So I always have to be careful of the signs, right? 25 negative plus 35, and I get 10. So the delta H of this reaction is 10 kilojoules per mole. Okay? And then it says it reacts with 2.5 moles of A. Well, 2 moles of A gives me 10 kilojoules of energy. Okay? So 2.5 moles of A for every 10 kilojoules per 2 moles. Okay? And that's going to help me determine how far I get. Okay? Does that make sense? Yes.
Does it matter that it's 2 moles of A2B?
No. I mean, 2 moles of A2B gives me this. Oh, no, not that. I'm sorry. Yeah, 2 moles of... It's actually just 1 mole of A2B. Here. This is the reaction we're looking at. This gives us 10 kilojoules. This 2 moles of A2B here, one of them can't. So I just have 1. Okay? Because they're telling me for these two, I have this energy. But then one of those cancels in. Yeah, you would have those delta H's and whatever you need on the questions. Yeah. Okay. Now, if I did have to reverse a reaction, what would I do to the delta H here? I would change the sign. If I had to multiply this by 2, what would I do to the delta H? Multiply it by 2. So whatever you do to the reaction, you have to do to your delta H. And that's Hess's law. Just reorganizing that. Okay.
And then I was also